So previously we have defined the class CSR, the class of conflict serializable schedules, and we did the modeling of this over so-called conflict relation, which was inducing then in the end the conflict graph. We had to check for being acyclic to see if the schedule is conflict serializable. What we do now is to look at another concept which is called commutativity-based equivalence. The idea here is when you're looking at a schedule, for instance, you have R1 of X and writing of Y, you see that these are not in the schedule, not in conflict. So nothing would be wrong when we assume we can just swap them. And if we swap them, we get another schedule, and the schedule is still conflict equivalent to our initial schedule, because it would still preserve our conf relation of our schedule, right? So we can allow some of these changes, some of these swap operations in our initial schedule S. And if we are not swapping conflict operations, but we only swap those which are not in conflict, this is still preserved. The idea behind commutativity-based equivalence, in order to derive if some schedule is conflict equivalent with a serial schedule, is to see if we can apply a number of these swap operations to our schedule S and obtain in the end a serial schedule. So this is more like a constructive way to show something is conflict serializable, in contrast to the serializability graph testing from before. Okay, definition: commutativity-based equivalence. We have two schedules, S and S prime. The operations within the schedule should be the same. This makes sense, right? I should talk about the same operations. Then S and S prime are so-called commutativity-based equivalent, denoted by this S tilde star S prime, if S prime can be derived from S by a finite number of applications of rules C1 to C4. And these rules, at least C1, 2, 3, are exactly these swapping rules which are allowed and still preserve conflict equivalence because they're not modifying this conf relation. Let's have a look at the first three of these rules. They say when you can swap. And the rules which are not here because they're not allowed, these are the rules which were not allowed because you would mess up with this conf relation. So let's see how they look like. So C1 says you can swap two reads from different transactions. See, so there's Ri of X and Rj of Y, and you can swap them into these two. And we understand now by the previous discussions that you can do that, and if you have initially a schedule S and you're applying this rule C1 and you're getting a schedule S prime, let's say, then these two have still the same conf relation, right? Because we did not mess up with conflict operations because reading is not in conflict. Also, what C2 tells us, we can swap read and write, but only if the objects we are reading and writing are not the same. Yeah. Also, this is not messing up with our conf relation. And C3 says we can also swap writes, but be careful, there have to be different objects we are writing to. So this means that applying these rules separately or sequences of these rules, they're preserving, of course, the operations within the schedules because we're not dropping any operation, and they're preserving the conf relation for these. And the idea in the end is that we have a schedule S, and by applying a sequence of these swaps, we end up with a serial schedule, and then we can say that the initial schedule is conflict serializable. This one here we can ignore for now, or in general we can ignore that. I want to just put it here because we also defined partial schedules in the definition of schedules and also the partial order for the individual transactions. So this kicks in these cases, but for us now, since we usually talk about these sequences of operations as schedules, the order is given, and then we're interested here in C1, 2, and 3. So let's now see how we can apply these rules to turn S into a serial schedule, and we see already the solution is here. We end up in the end with the serial schedule T1, T2, T3. But how do we come to this? Well, let's have a look at the initial schedule S. And we see here we have a mix of things from transaction 2 and 1. And we could think about swapping these two, and in fact we can do this because they are on different objects. Here we have X and here we have Y. So we can swap these. And we can also swap these two. We have a read and a write. Be careful, but no problem, because here we have Z and here we have Y. So we have this here and this here. The consequence changed. And we are not done yet because the schedule here is not serial yet, because we still have some mixtures between transaction 2 and 1, namely here. But we can also swap these two because it's on different data objects. And the remaining schedule is anyway fine, because here we have in the end transaction 3. This is the only thing we have to fix here, and we did it. So now we have here everything from transaction 1, everything from transaction 2, and everything from transaction 3, which is exactly this serial schedule. And in our understanding that we never mess up with our conflict relation, we somehow see that every step we're doing from this S to S prime to S prime prime, if you want to call it like this, is always preserving this conflict equivalence. So that means S is conflict equivalent to this, in the end, serial schedule, and hence S is conflict serializable. The multiple application of these swapping steps can also be formulated as so-called commutativity-based reducibility. So if you have this S and you have a serial history S prime, and you can reach S prime by multiple of these swaps, or one or multiple, then we say S is commutativity-based reducible to this S prime, which is a serial history. And then, what I already motivated, we have the following theorem. If we have S and S prime to be two schedules with the same operations, then S is conflict equivalent to S prime if and only if S is commutativity-based reducible to S prime. And this also should not be difficult to understand why this is true, because of my explanation before that we're not changing the conflict relation in any way, not the operations of S and S prime. Then we have the following corollary. History S is commutativity-based reducible if and only if S is in CSR. And one remark, because we later on will also see how we're implementing a scheduler which is called two-phase locking. Two-phase locking is exactly doing or allowing these schedules that fall into CSR.